Hi, welcome to our channel of IGNOU Audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Diploma Postgraduate Diploma Programs. Postgraduate Diploma in Analytical Chemistry, PGDAC. MCH-001 Basic Analytical Chemistry. Block-1 Basic Aspects. Unit-1 Analytical Chemistry General Perspective. 1.1 Introduction. Analytical chemistry is a subdiscipline of chemistry with interdisciplinary character. This is the first unit of this program. In this unit, we will first learn about the analytical chemistry. We know the importance of chemicals in our life. Chemicals are the foods we eat, clothes are made up of chemicals, and medicines are full of chemicals, and so on. We all know the importance of chemical analysis in all these products. The development of methods for chemical analysis lies in the province of analytical chemistry. Therefore, in this unit first we will learn about the analytical chemistry and its importance. Then we will study about different chemical methods of analysis like gravimetry and volumetry analysis. We will also discuss briefly about the classification of electrical methods of analysis, which include potentiometry, amperometry, voltammetry, colorimetry, etc. In the latter part of the unit we have introduced you to optical method of analysis like emission, absorption, UV, IR, and Raman spectroscopic. We have also discussed nuclear and thermal methods of analysis briefly. Separation of the chemicals compounds is a very important part of analytical chemistry. So we introduce you about the separation methods. There is a separate course on separation methods, i.e. course MCH-002 in this PGDAC program, where you will study all these techniques in details. In the last you will study emerging needs and recent trends of analysis. Objectives. After studying this unit, you should be able to times broaden your perception of the field of analytical chemistry, times distinguish between various analytical techniques, times classify the chemical, electrical, optical, nuclear, and thermal methods of analysis, times classify the separation methods, times understand the utility of analytical techniques, and times highlight the development of methods of chemical analysis. 1.2 Analytical Chemistry and Introduction. In our daily lives, we cannot help but make use of chemicals. Chemicals are the food we eat, these are the clothes we wear, the medicines we take, and the immense variety of articles that we use. As a chemist, whenever you see a material, to curiosity, questions are raised in your mind: what is it? And how much? The answer of these questions is given by chemical analysis. In chemical analysis, you are able to analyze compounds to see what and how much of a given chemical constituent they contain. However, before an analysis can be made, a method must be available. The development of methods for chemical analysis lies in the province of analytical chemistry. In developing methods of analysis, the analytical chemists try to use the principles from any field of science: chemistry, physics, biology, biochemistry, geology, engineering and computers, etc. The constituents to be analyzed may be elements, ions, radicals, functional groups, or compounds. Analytical chemistry is thus concerned with the theory and practice of methods used to determine the composition of substances. At the present time, no material is taken into production or released without analytical data which characterize its quality and suitability for various purposes. The qualities of food, materials, and medicines, etc. all need analysis results prior to be used. These results not only form the basis of all processing calculations, but they also determine the costs of materials, which form the basis of financial estimates. This makes an analytical laboratory as an important section of chemical industry. The last 3 to 4 decades witnessed an exciting phase in the development of analytical chemistry in terms of new and improved analytical techniques which permit separation, detection, structure elucidation, and quantification of much lower levels of chemical species, multi-component analysis, and a much short duration required for analysis. Analytical chemistry is a chemical discipline with interdisciplinary character. The analytical methods can be divided into 3 major groups. They are chemical, physical, and physicochemical methods. The chemical methods are the classical methods, whereas the physical and physicochemical methods are known as instrumental methods of analysis. A method to be called as an analytical technique should be based on the measurement of a property which is related to either the nature or the amount of the substance under examination. The analytical chemist must understand the relation between the property to be measured and the nature and the quantity of the desired chemical species to be studied. The property which depends on the nature of the substance is helpful in qualitative analysis, whereas the property which depends on the amount of the substance is useful in quantitative analysis. Mostly a quantitative analysis is preceded by the qualitative analysis, while a qualitative analysis may give a rough idea of the relative amount of the constituents present in the sample. The sample is the part of the material which is examined. In analytical chemistry, we take small samples to perform the chemical analysis, and these results are taken as a measure of the results of whole material. A substance can be determined by a variety of methods, and the analytical chemist then has to select the most advantageous method available in the laboratory. For choosing a suitable technique, the analyst must know what type of samples is to be analyzed, what information is needed, and for what purpose. Further, the way you perform an analysis will depend on your experience, the equipment available, and the preparation of the sample for analysis, the time and the cost involved. Besides this, you have to choose an analytical method on the basis of accuracy, sensitivity, and selectivity. While choosing an instrumental technique, you should be aware that most instrumental methods are relative methods. Therefore, they must be calibrated with standards. Usually, an analytical calibration curve of instrument response versus concentration or amount of the substance is prepared prior to analysis of unknowns. 1.3 Classification of different analytical techniques. Analytical chemistry deals with the development of methods for chemical analysis. These methods depend on the measurement of some physical property. Various physical properties which are characteristics of a particular substance or its constituent can be made the basis of an analytical technique. A listing of the types of analytical techniques demands some kind of classification. Classification schemes will vary with the viewpoint the analytical chemist considers. In the broader sense, the analytical techniques can be classified on the basis of type of properties in the following way. 1. Chemical methods of analysis. 2. Electrical methods of analysis. 3. Optical methods of analysis. 4. Nuclear radiation methods of analysis. 5. Thermal methods of analysis. 6. Separation methods. These methods can further be classified into different techniques depending on the measurement of a characteristic property based on either the nature or the amount of the desired constituent of the sample. 1.3.1 Classification of chemical methods of analysis. These methods are based on the primary role of a chemical reaction. In these methods, the direct measurement of mass is carried out by one of the two procedures, i.e., by weighing or by measuring volume. The corresponding methods are known as gravimetry and volumetry. Both of these being developed at early stage are now also known as classical methods of analysis. Gravimetry. Gravimetric analysis means analysis by weight and pertains to all determinations, wherein the final results are obtained by means of the analytical balance. Gravimetry is an accurate macroanalysis procedure which mainly depends upon precipitation of an ionic or molecular substance on the basis of a chemical reaction. The precipitate is then separated, dried and weighed in the suitable form. The amount of the desired constituent, analyte, is then determined by simple calculation. At undergraduate level you have estimated barium as barium sulfate following gravimetric analysis. Volumetry. The amount of the analyte can also be found in another way by measurement of the volume. The method based on accurate measurement of volume of a reagent solution of accurately known concentration taken for a reaction is known as volumetric analysis. The measurement of volume makes considerable saving of time. The greater speed of volumetric analysis is an important advantage of this method over gravimetry. The volumetric analysis is characterized by a titration, hence the method is also known as titrimetry. In this method, a known volume of the reactant substance is taken in a beaker and the titrant is added from a burette to it till the reactant completely reacts with the titrant. We call it as the equivalence point, which is indicated by an indicator. The volume of the titrant required to reach the equivalence point is noted on the burette and the calculations are made to get the amount of the constituent of the reactant. The volumetric method is much simpler than the gravimetric method. However, the reaction for volumetry should be rapid, so that, practically speaking, zero time will be needed after each volume addition of titrant for the reaction to reach equilibrium. 1.3.2 Classification of electrical methods of analysis. An electrical method of analysis, also known as electroanalytical method, can be defined as one in which an electrochemical property of a solution is measured. A classification of electroanalytical methods can be made by measuring different electrical quantities such as potential, current, quantity of current, resistance and dielectric constant. These methods have different names on the basis of the measurement of these quantities and are stated below. 1. Potentiometry. 2. Amperometry. 3. Voltammetry. 4. Coulometry. 5. Conductometry and high-frequency methods. 1. Potentiometry. Analytical methods based on the measurement of potential difference across an electrochemical cell to interpret the results of an analysis are designated by the term potentiometry. The term potentiometry is derived from the word potential, which is valve cell potential, electrode potential, obtained by measuring voltage across an electrochemical cell with the help of a standard electrode. The result of the analysis can be computed directly from the voltage of the cell or the equivalence point of a titration known as potentiometric titration. In potentiometric titrations, we discuss redox titration curves based on half cell potentials and describe the necessary procedures to obtain the sample analyte in the correct oxidation state. For titrations, a special class of potentiometry where the potential of an indicator electrode is measured as a function of hydrogen ion concentration is designated as pHmetry. By suitably modifying the common voltmeter to high impedance MV meter and usually making use of a glass electrode as a hydrogen ion indicator electrode, suitable p-meters can be designed to measure pH instantaneously. 2. Amperometry. Amperometry designates methods involving current measurements. The term Amperometry is derived from the word ampere, which is the unit of current. Amperometric methods are generally applied to the detection of equivalence point of titration, and method is known as amperometric titration and usually involves one microelectrode as an indicator electrode, which is also polarized electrode. The other electrode is the reference electrode and is non-polarized. Here the current at a fixed potential is measured as a function of titrant volume. On plotting the data to straight lines with different slopes are obtained on both the sides of equivalence point. A modification of the amperometric titration involves the use of two polarized microelectrodes and is known as biamperometry or the dead stop endpoint titration. Here the two identical microelectrodes are immersed in a well-stirred solution of the sample. A small potential is applied between these electrodes and the current is measured as a function of the volume of the titrant added. 3. Voltammetry. In voltammetry, an electroactive species is consumed, oxidized or reduced only at the surface layer of the indicator electrode in an electrolytic cell. The resulting current, due to electron transfer process, is measured as a function of applied potential. The current versus potential curves are plotted. These curves are known as the current voltage curves or current potential curves or IE curves. The shape of the IE curves depends on the polarization of the indicator electrode, whereas the other electrode known as the reference electrode remains non-polarized. In voltammetry, we study the relationship between the current and electrode potential and its application to chemical analysis. When a special type of microelectrode, the dropping mercury electrode, is used as the indicator electrode, the technique is known as polarography. A continuous changing potential is applied across the dropping mercury electrode and the reference electrode, and the resulting current is monitored by a current measuring device. The potential curves are known as polarograms or polarographic waves. The half-wave potential, E half, of a polarographic wave can be a useful quantity for qualitative identification, whereas the height of the wave is used for quantitative estimation of the particular species. A recent development in polarography has been made by the use of 3 electrodes. This modification makes it possible to obtain sharply defined polarographic waves from non-aqueous solvents that have low electrical conductivities. 4. Colorimetry. Analytical methods based on the measurement of the quantity of electricity are designated by the term colorimetry. The term is derived from coulomb, which is one of the units used for quantity of current. A fundamental requirement of all colorimetric methods is that the species determined interacts with 100% current efficiency. Colorimetry is performed by two general techniques: I. Colorimetry at constant potential, known as potentiostatic colorimetry, and 2. Colorimetry at constant current, known as amperostatic colorimetry. In the first, the potential at the working electrode, the electrode at which the analytical reaction occurs, is maintained at a controlled level. Here current is initially high and decreases exponentially with time. In the second, that is, colorimetry at constant current, a constant current is operated for a time until a signal indicates the completion of the analytical reaction. These methods are frequently called colorimetric titrations. The second type of methods has enjoyed wider applications than the first. 5. Conductometry and high-frequency methods. The measurement of conductance, the reciprocal of the resistance, can sometimes be useful in chemical analysis. Methods based on electrical conductance measurements are grouped under the term conductometry. Conductometry is performed in two different ways. In one, an analysis can be computed directly from conductance measurements, and in other, conductometry is applied to the determination of the equivalence point of titrations, conductometric titrations. Conductometric titrations, where the change in conductance is related to concentration changes of the ionic species involved in the titration reaction, are more frequently applied. In conductometry, conductances are generally measured by using alternating current of 3 to 6 volts with frequency of 50 to 1000 Hz. The technique has the advantage of simplicity and good sensitivity. In conventional conductometric method, as stated above, conductance measurements are made by using alternating current at relatively low frequencies, 50 to 1000 Hz. The technique can be modified by using much higher frequencies, several megahertz, and the methods are called as high-frequency methods. These methods can be applied to the measurement of dielectric constant and also for several titrations where the electrodes do not come in the intimate contact of the solution. 1.3.3 Classification of optical methods of analysis. In subsection 1.2.2 you have studied the classification of electroanalytical techniques. In this subsection you will study the classification of optical methods of analysis. Briefly, in course MCH-003 of this program you will study optical methods of analysis in details. These methods are now called as spectroscopic methods of analysis. In these methods the first instruments were developed for use of visible region and therefore called optical methods. This term has by now been extended to other regions of EMR as well. All spectroscopic methods are based on the interaction of electromagnetic radiation with the quantized energy states of the matter. Here we study the measurement of a quantity based on emission, absorption, scattering or change in some property of electromagnetic radiation, EMR, depending on the nature or the amount of the constituent of the sample. The classification may be based on either the type of effect, emission, absorption or scattering, or the type of the EMR, X-ray, UVs, IR, etc. used. The important spectroscopic methods are mentioned below. 1. Emission spectroscopy. 2. Absorption spectroscopy. 3. Ultraviolet and visible absorption spectroscopy. 4. Infrared absorption spectroscopy. 5. Fluorophotometry. 6. Turbidimetry and nephelometry. 7. Raman spectroscopy. 1. Emission spectroscopy. Emission spectroscopy is the method where the characteristic spectrum produced by excitation of elements is applied to qualitative and quantitative analysis. These methods depend on the electromagnetic radiation produced when the analyte is excited by thermal, electrical or radiant energy. Each element has a characteristic emission spectrum. This is applied to qualitative analysis. Quantitative determinations are also possible, as during the burning of the sample under controlled conditions the energy emitted for a given spectral line of an element is proportional to the number of atoms that are excited and consequently to the concentration of element in the sample. 2. Absorption spectrometry. Absorption spectrometry is based on the measurement of the absorption of electromagnetic radiation by matter. Absorption refers to a process by which a chemical species in a transparent medium selectively absorbs the photons of certain electromagnetic radiation. The absorption varies with the wavelength of incident radiation. Measurement of absorption can be made at single wavelength or over a wide range of wavelengths. When the selection of a narrow wavelength range is made with the help of filters, the analytical technique is known as filter photometry. When the measurements are made for approximately monochromatic radiation obtained with the absorbances are easily measured in each spectral region and are of great utility in analytical studies. The various types of spectroscopic methods are also named on the Basis of the spectral region used. 3. Ultraviolet and visible absorption spectroscopy. Analytical methods which involve the measurement of absorption of ultraviolet and visible radiation, wavelength range from 180 to 780 nanometers, by an atomic, ionic, or molecular species are known as ultraviolet and visible spectroscopic methods. UV and visible spectroscopy involves transitions between electronic levels of absorbing chemical species. These methods find application in qualitative as well as quantitative analysis.
For qualitative analysis, UV visible spectra provide a valuable tool in the identification of unsaturated organic compounds and elucidation of their structure. However, these methods, particularly in the visible range, are mainly used for quantitative analysis of substances of different categories. Help of a monochromator, such as prism or grating. The technique is known as spectrophotometry or absorption spectrometry. 4. Infrared absorption spectroscopy. Infrared absorption spectroscopy involves the absorption of infrared radiation. Wavelength range from 0.78 to 1000 micrometers, depending on increasing the energy of vibration or rotation associated with a covalent bond, provided that such an increase results in a change in the dipole moment of the molecule. Infrared (IR) spectroscopy can further be subdivided into near IR, middle IR and far IR spectroscopy. Majority of applications lies in the middle IR region. IR spectroscopy finds widespread application to qualitative and quantitative analysis. However, its most important use has been for the functional group identification of organic compounds. 5. Fluorophotometry. The energy of the photons of incident radiation absorbed and changes the absorbing species to excited state. Certain chemical substances, known as photoluminescent, after excitation can re-emit radiation. Re-emission of radiation can be immediately less than 10 to 8 seconds after the absorption and is known as fluorescence. The fluorescence intensity is practically proportional to the concentration of fluorescent substance. The measurement of the intensity of fluorescence serves useful analytical purposes and the technique is known as fluorophotometry. When re-emission of radiation takes longer time, minutes, hours, or days, the phenomenon is known as phosphorescence and the related technique as phosphorimetry. 6. Turbidimetry and nephelometry. These methods are applied to determine the concentrations of suspensions where small solid particles are homogeneously dispersed in the liquid medium. Analytical method, where determinations are made by measuring opacity of suspension of small particles with the help of measuring intensity of transmitted light, is known as turbidimetry. The analytical method, which is based upon the measurement of intensity of light scattered by a suspension of small particles, is designated as nephelometry. Turbidimetric and nephelometric methods frequently give erratic results. Therefore, these methods are applied only when the results need not to be very accurate and other precise methods are not available. 7. Raman spectroscopy. Raman spectroscopy involves the scattering of electromagnetic radiation by a liquid solution, following Raman effect, scattering with change of wavelength. The shift in wavelength in Raman effect is caused due to extraction of energy from the quanta of incident radiation and utilized to raise molecules to higher vibrational states. The scattered radiation thus has less energy and higher wavelength. Raman and infrared techniques concern vibrational energy change and they are complementary to each other. An important advantage of Raman spectra over IR spectra lies in the fact that water does not interfere in Raman spectroscopy and aqueous solutions can be handled very well. Some other optical methods, namely flame photometry, refractometry, polarimetry, find applications in analytical laboratory but are not considered due to their less importance. 1.3.4 Classification of nuclear methods. We shall now examine some techniques which can provide analytical information based on nuclear properties. Each of these properties or combinations of them can be studied suitably by analytical chemistry. Nuclear method can be grouped into following: 1. Radiochemical methods. 2. Radiometric methods. 3. Isotopic dilution methods. 4. Activation analysis. 5. Mossbauer spectroscopy. 6. Nuclear magnetic resonance spectroscopy. 7. Mass spectrometry. Table 1.1 lists these methods along with the property measured. Table 1.1 Nuclear methods of analysis. Look at the screen. 1. Radiochemical methods. Very small amounts of radioactive substances having natural or artificial radioactive isotopes have measurable activity. This makes the development of sensitive analytical methods known as radiochemical methods. Radiochemical methods are classified into three categories, namely radiometric analysis, isotopic dilution methods, and activation analysis. All these methods have high sensitivity, specificity, and good accuracy. 2. Radiometric methods. In radiometric methods, a radioactive reagent is employed to separate the analyte completely from the bulk of the sample. The activity of the isolated material is then measured. In an alternate way, when a radioactive reagent is used to literate the analyte and the endpoint is established by activity measurements, the method is known as radiometric titration. 3. Isotopic dilution methods. In an isotopic dilution method, a known amount of the same substance containing an active isotope is added to the unknown and thoroughly mixed with it. A sample of the pure substance is then isolated from the mixture and its activity is measured. The quantity of the substance in original material is then determined by simple calculation. The technique is suitable where a compound can be isolated in pure state, maybe with only a poor yield. Isotopic dilution method has the advantage of not requiring quantitative separation of the analyte. 4. Activation analysis. The methods of activation analysis are based upon the measurement of radioactivity induced in the samples by irradiation with suitable particles such as neutrons, protons, deuterons, or helium-3 ions. However, thermal neutrons from a nuclear reactor are the most commonly used particles, and this technique is known as neutron activation analysis. 5. Mossbauer spectroscopy. The analytical methods based on the study of the phenomenon of the resonance fluorescence of gamma rays are known as Mossbauer spectroscopy. It involves intranuclear energy levels. An important characteristic of this radiation is the extreme sharpness of lines. 6. Nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance (NMR) spectroscopy is based upon the measurement of absorption of electromagnetic radiation in radio frequency region by nuclei of atoms of certain elements, isotopes, in the influence of strong magnetic fields. Since a nucleus bears a charge, its spin gives rise to a magnetic field. The resulting magnetic dipole is oriented along the axis of spin and has value based on the nature of the nucleus. As a consequence, certain atomic nuclei on exposure to a magnetic field would lead to splitting of their energy levels. The position of the signals of NMR spectra is characterized in terms of chemical shift, which is very useful in structure elucidation. An analogous method called electron spin resonance (ESR) is based upon the absorption of microwave radiation by an unpaired electron when it is exposed to a magnetic field. 7. Mass spectrometry. Mass spectrometry is a method based on the study of converting molecules into charged particles, molecular ions, their separation on the basis of mass to charge ratio, and measurement of the relative intensity of lines of mass spectrum. The instrument used is a mass spectrometer which separates the charged gas molecules, ions, according to their masses. Mass spectrometry is capable of providing qualitative and quantitative information about either the atomic or the molecular composition of the sample. It is an important tool for elucidating the structure of organic compounds. 1.3.5 Classification of thermal methods of analysis. In thermal methods of analysis, some property of the system is measured as a function of temperature. In some of these methods, the temperature is used as an independent variable, while in some others as a dependent variable, say time. The recorded curves are helpful in interpreting the thermal behavior of the sample. Thermal methods are classed into nearly a dozen varieties. Out of these, some commonly used methods are 1. Thermogravimetric analysis, TGA. 2. Derivative thermogravimetry, DTG. 3. Differential thermal analysis, DTA. 4. Differential scanning calorimetry, DSC. 5. Thermometric enthalpy titrations, TET. Property measured and instrument used for these methods are given in Table 1.2. Table 1.2, Thermal methods. Look at the screen. 1. Thermogravimetric analysis, TGA. Thermogravimetric analysis, TGA, involves the measurement of mass of a sample as its temperature is increased at a linear rate. In TGA, a suitable solid sample undergoes the following type of reaction: reactants products plus gas, causing a loss of mass due to gas being evolved. Plot of mass versus temperature, known as thermogram, pursues determination of thermal stabilities and sample compositions at different temperatures. 2. Derivative thermogravimetry, DTGA. Derivative thermogravimetric analysis, DTGA, as the name suggests, is carried out by the plot of first derivative of thermogram. In DTG, a plot is prepared in dW/dt versus T. In DTG curves, the changes are observed in the form of maxima or minima, which make the weight changes very clear, even those which are not so clear in thermograms. 3. Differential thermal analysis, DTA. In differential thermal analysis, DTA, the difference in temperature between sample and reference is measured as a function of temperature. From the plot of T versus T, the transition temperature and the nature of the change, exothermic or endothermic, can be determined. 4. Differential scanning calorimetry, DSC. In differential scanning calorimetry, DSC, the sample and the reference material are subjected to precisely programmed temperature change. When a thermal transition occurs in the sample, the temperature changed is balanced by adding thermal energy to either the sample or the reference. DSC can measure directly both the temperature and enthalpy of a transition. 5. Thermometric enthalpy titrations, TET. The thermochemical methods where a titration process is followed by the measurement of enthalpy change during the course of a reaction carried out under controlled conditions, usually in a small Dewar flask, are known as thermometric enthalpy titrations. The above lists do not conclude all the methods of chemical, physical and physico-chemical methods of analyses. Useful analytical determinations can be made on the measurement of various other properties such as refraction, reflection, surface tension, polarization of light, etc. However, such methods are not listed here just for the sake of convenience. 1.3.6 Classification of separation methods. In the previous subsections 1.3.1 to 1.3.5 you have learnt that the determination of a substance which is free from interfering substances can be accurately made by the direct application of the suitable technique. However, in natural samples the state of affairs is likely to be much different because of their complex nature by the presence of interfering substances. Extremely few methods may be specific or even selective, and accuracy in determinations by most methods are affected by the interfering substances. It is, therefore, frequently necessary to perform quantitative separations, with the objective either for isolation of the analyte or to remove the interfering substances. Therefore, separation is a prerequisite procedure for such determinations. Though separation is not a purely analytical technique, but it is commonly required prior to many analyses. You will know about some methods of separations in this subsection. In separations, in general, by appropriate reactions, the desired constituent is brought into one phase, and interfering elements are brought into another, and the phases being separated by physical processes. Some methods of separation are the following. A. Classical methods. A. Precipitation. B. Distillation. C. Sublimation. D. Formation of complexes. B. Modern methods. 1. Chromatography. 2. Solvent extraction. 3. Ion exchange. 4. Electrophoresis. You are well aware about the classical methods, and only the modern methods will be defined here briefly, and in course MCH-002 you will learn these methods in details. 1. Chromatography. Chromatography is a multi-stage separation process in which the sample is applied on a stationary phase over which a mobile phase is percolated. Various solutes present in the sample are separated on the basis of differential migration. Chromatography can be classified into various kinds depending on the nature of stationary and mobile phases and the mechanism of distribution involved. These kinds are named as paper chromatography, thin layer chromatography, liquid chromatography, high performance liquid chromatography, gas chromatography, gel chromatography, partition chromatography, adsorption chromatography, ion exchange chromatography, electrochromatography, etc. Chromatography has been used with remarkable success in the separations of inorganic, organic and biochemical substances. The separations of vitamins, hormones, natural pigments, fission products of uranium and steroids, etc. are some good examples of its scope and success. 2. Solvent extraction. In solvent extraction, a desired solute can be isolated/extracted by distributing it between two immiscible liquids. It exploits the differential solubility of a given solute in two immiscible solvents to separate it from the given mixture. Solvent extraction can be applied as a single-stage procedure or a multi-stage procedure. Counter-current extraction. 3. Ion exchange. Ion exchange is a stoichiometric process in which a solid, insoluble material, known as ion exchanger, when comes in contact with an electrolyte solution, takes either positive or negative ions, known as counterions, and releases the ions of like charge to maintain the stoichiometry to the solution. The solid materials having cations as exchangeable ions are known as cation exchangers, and having anions as exchangeable ions are known as anion exchangers. Ion exchange is a reversible process. The exchanged ions can be replaced by other ions of like charge. Ion exchangers find great utility in separating the ionic species of similar nature. Some separations of common interest are of rare earth elements and of amino acids. 4. Electrophoresis. The movement of charged particles in the influence of an electric field, in general, is known as electrophoresis. If the components of a mixture have different velocities under the influence of the electric field, it is possible to separate them. This method has been used with remarkable success for the separation and characterization of polysaccharides, nucleic acids, hemoglobins and other high molecular weight compounds. Small organic and inorganic ions can also be separated with the help of this technique, known as ionophoresis. 1.4 Criteria for evaluating the utility of analytical techniques. Analytical chemistry is of enormous importance in science and industry. It deals with the development of methods for chemical analysis which are utilized in detection, determination and separation of chemical constituents and structure elucidation of chemical compounds. For example, the chemical formula of an unknown substance is ascertained from the percentage contents of its constituents found by analysis. Today, with the help of newer techniques, such as mass spectrometry, NMR spectroscopy, high-performance liquid chromatography, etc., the structure elucidation has become more perfect. Utility of analytical techniques is to be found in various fields as the key to the solution of a variety of scientific problems and of industrial problems. It is a chemical discipline with interdisciplinary character providing valuable information in many branches of science and technology. All fundamental laws are based on analysis. Mechanisms in so many chemical reactions are developed as a result of analysis. Much of what is known of the mechanisms by which chemical reactions occur has been learned through kinetic studies employing quantitative measurements of the rates at which reactants are consumed or products are formed. You understand the importance of rates in an industrial process to decide the cost of the products coming out of an industry. The results of a typical quantitative analysis are based upon two series of measurements, one of which is related to the amount of sample taken, and the second to the relative amount of the desired constituent present in the sample. On the basis of the amount of the sample taken, the methods are named as macro, meso, micro, and ultramicro methods. On the basis of the relative amount of the desired constituent, the results take the form of numerical data in suitable units such as percent, parts per million, parts per billion, or some other form. In order to understand the criteria for evaluating the utility of the analytical techniques, it is useful to identify the several steps in performing quantitative analysis. A. Complete analysis actually consists of the following main steps. 1. Sampling. 2. Dissolution of the sample. 3. Separation of interfering substances. 4. Measurement. 5. Interpretation of the measurements. Often beginners carry out usually steps 3, 4 and 5, for the sake of convenience. 1.4.1 Sampling. The heart of the quantitative analysis is to carry a sample with great care through a number of manipulations without accidental losses and without introducing foreign material, since the sample is representative of all components and their amounts as contained in the bulk material. Conclusions will be drawn about the composition of the bulk material from the analysis of a very small portion of the material. A knowledge of statistics is of considerable importance as an aid to establishing sampling programs so that data obtained may be subjected to statistical treatment when necessary. Sampling techniques may be quite different in different cases. Each type of material has its own special sampling instructions which take into account the specific characteristics of the material, the quantity taken, its purpose, etc. 1.4.2 Dissolution of the sample. Most analyses are performed on solutions of the sample. Therefore, suitable solvent is required to dissolve the sample rapidly and under conditions in which there is no loss of the analyte. The dissolution process depends on the nature of the sample material. Two most common methods employed in dissolving inorganic sample are 1. Treatment with hydrochloric acid, nitric acid, mixture of hydrochloric and nitric acids, sulfuric acid or perchloric acid, and 2. Fusion with an acidic or basic flux followed by treatment with water or an acid. Organic solvents are preferentially taken to dissolve the samples of organic nature. However, special methods are to be developed to dissolve a silicate material, a high molecular weight polymer, or a specimen of animal tissue. 1.4.3 Separation of interfering substances. The interfering substances are the compounds or elements that prevent the direct measurement of the species being determined. Therefore, before an analytical measurement can be made, it is usually necessary to solve the problem of interferences by their separation from the analyte. There may be two ways in general to achieve separation: I, by isolating the desired constituent in a measurable form, or 2, by removing the interfering substances from the desired constituent. In most of the separation techniques, the substance of interest is transferred from one phase to another. Therefore, the separation procedures can be classified depending on the type of phases involved in these procedures. There may be 4 such combinations: solid-liquid, liquid-liquid, solid gas and liquid gas. 1.4.4 Measurement. The way of measurement depends upon the type of analytical technique being used. A gravimetric method involves the measurement of weight of a suitable form of the analyte. In a volumetric method, the measurement is of the volume of a solution of known concentration which is required to react with the analyte. A characteristic feature of most instrumental methods is the necessity for finding empirically the value of the intensity factor corresponding to the mass or concentration of a given constituent. The majority of these methods, therefore, require calibration by the use of a standard containing a known amount of constituent, which serves as a basis for comparison in the measurement. The established procedure must be followed carefully in individual quantitative determinations. Equal care must be taken in the choice of suitable technique for the desired determination. The success or failure of an analysis is often critically dependent upon the proper selection of method. The analytical chemistry can save much time and improve the accuracy of results by a critical comparison of the various methods on the basis of certain criteria. Although no simple rule can be prescribed, but some essential characteristics of a method which must always be considered are the following: A. The complexity of the materials to be analyzed. B. The probable concentration of the species of interest. C. Accuracy. D. Sensitivity and detection limit. E. Selectivity. F. Duration of an analysis. G. Cost of equipment. 1.4.5 Interpretation of the measurement. The result of an analytical measurement after proper calculation is usually reported in relative terms, that is, in some way that expresses the quantity of the analyte present per unit weight or volume of the sample. Thus the results take the form of numerical data in suitable units such as percent, parts per million, or some other. The methods of statistics are commonly used and are especially useful in expressing the analytical results. You should remember that the analytical results can be reliable only if all the conditions for which the particular method was developed and verified are strictly obeyed. Any deviation from these conditions leads to error and loss in accuracy. 1.5 Emerging needs and recent trends. Analytical chemistry is of fundamental importance as it is based on the development of methods for identification, determination and separation of substances in different ranges, be it a major or a trace constituent. Identification of a new compound and its structure elucidation, for example, need the result of chemical analysis for its confirmation. It is impossible to understand a chemical reaction without knowing the quantities involved. The study of the mechanisms of all chemical reactions at one stage or the other requires the use of analytical chemistry, side by side with its use in the development of fundamental aspects of science. Analytical chemistry finds its need in the day-to-day life of the people. Today there is a great need of chemical analysis in industry, since it provides the means of testing raw materials and for assuring the quality of finished products. Most industrial products such as fuels, paints, pharmaceuticals, food materials, etc., cannot be sold to the consumer without the analysis information written on the label of the product. It is the analytical chemistry which decides whether or not an ore can be used for profitable extraction of an element, whether a product manufactured in an industry is under quality control or not. Not only in chemistry but in such diverse branches of science as physics, biology, mineralogy, medical sciences, geology or technology, etc., analytical chemistry is required in the solution of many intricate problems. Analytical chemistry is recognized to fulfill both the fundamental as well as the applied aspects of science and technology in general and chemistry in particular. The explosion of industrial and technological developments in recent years has created analytical problems which demand increasingly sophisticated knowledge and instrumentation for their solution. You might have heard about a number of problems where the determination is required at parts per million or even parts per billion level. Some typical examples of such problems can be mentioned as determination of impurities at parts per billion levels in semiconductor materials, determination of pesticide residues at the trace level in food products, detecting traces of pollutants in the environment, analyzing a blood sample, or analyzing a giant protein molecule for several amino acids present in it. The solutions to such problems have successfully been developed by analytical chemists. At early stage you have gone through the study of the fundamental laws of chemistry. You know that they are based on quantitative analysis. The earliest analytical determinations systematically developed were based on the determination of the mass of a constituent. Antoine Lavoisier has been considered the father of analytical chemistry because of the careful quantitative analysis he performed on conservation of mass, using the analytical balance. Historically, the first quantitative analyses were gravimetric, made possible by the invention of precise balance. Gravimetric analysis means analysis by weight, was properly developed in the 17th century. Soon after the development of gravimetric analysis, it was found that carefully calibrated glassware made possible considerable saving of time through the volumetric measurement of standardized solutions. This technique is known as volumetric analysis or titrimetry. Both gravimetry and volumetry are capable of high accuracy but are valuable for major constituents. These methods are inherently simple, involve no prior calibration, no investment in expensive equipment and no high degree of specialized knowledge. These methods remained for many years the only quantitative procedures available for nearly all analyses. These methods are now known as classical methods of analysis. The methods developed mainly in the last century are known as modern methods of chemical analysis. In general, a technique at early stage is first developed. A few people become familiar with the new technique, they develop it for their own ends and the new methodology spreads throughout their field. The modern methods are classified into two groups: A. Non-instrumental, B. Instrumental. The non-instrumental methods are mainly the methods of separation that are required prior to analysis, and the important ones are chromatography, ion exchange, electrophoresis and solvent extraction. Although there is no clear demarcation between non-instrumental and instrumental methods, the difference is just of degree. The instrumental methods are more sophisticated as the instruments are composed of rather complicated electronic, optical and mechanical parts. In instrumental techniques, the principles of physics and physical chemistry are applied to study a particular property as a function of nature or amount of the substance of interest. The function of an instrument is to translate the chemical composition into information directly observable by the operator. The interest in instrumental analysis has been increased, mainly because of two reasons. A. They greatly reduce the duration of many analyses which are quite tedious and much time consuming by classical methods. B. They can be applied to the determination of substances under conditions in which classical methods fail, e.g., trace analysis. Instrumental methods are developed only recently, mainly because of two reasons. Firstly, the physical properties on which these methods are based were not known earlier. Secondly, the design of the instrument required a lot of investment. Furthermore, for every physical property to be measured, a separate instrument is to be designed, e.g., a spectrophotometer to measure absorbance, a pH meter to measure pH, and a conductometer to measure conductance. The invention of spectroscope brought with it an extremely fruitful analytical approach, and gradually a few colorimetric methods were investigated. After that, it was found that electrical measurements could detect endpoints in titrations, and several electroanalytical methods were developed. Somewhere in the middle of the last century, the rapid development of sophisticated instrumental components, vacuum tube amplifier, photoelectric tube, photomultiplier tube, transistors, semiconductor devices, etc., has resulted in the establishment of many analytical instruments based upon them. The recent trends in analytical techniques have followed closely the development of new measuring instruments to find faster and convenient ways for sensitive and selective determination of desired constituent. Today we have a number of instrumental methods which can analyze in minutes what was done in days before. Not only the time has been shortened, but with the help of new techniques it is now possible to detect and determine trace constituents at micro and nano or still lower levels, and to analyze mixtures which could not be analyzed by the earlier methods. Thus, there have been three major contributions in the present vitality of analytical chemistry. 1. The flow of theory from physical chemistry and physics into analytical chemistry. 2. Application of electronics by analytical chemists for assembling new, faster and more sensitive instruments. 3. Application of computers for both data processing and automated control of instruments. Such contributions have resulted in an explosive development in regard to the kinds of samples to be analyzed and the sensitivity of the identification and determination of the analyte. This also resulted in a great decrease in time and human labor required for each determination. One of the recent developments in analytical chemistry during the last few decades has been achieved by the appearance of commercial automatic analytical systems. Here the ready-made analytical data is provided in a much smaller time with minimum efforts of the operator. Initially these systems were applied for routine analyses of clinical laboratories. Now, they find their utility in diverse fields of routine chemical analysis and control of industrial processes. Often the analysts have to handle a large number of samples and are required to process vast amounts of data. Instruments can be designed that will automatically perform many or all the steps of an analysis. Computer techniques can be applied or even be interfaced to the analytical instruments, and the results can be automatically interpreted as desired. Such automation is very helpful to get continuous online analytical information of the quality control of an industrial plant process. Now it is possible to perform all steps of an analysis starting from sampling through measurement to data display using automatic analytical instruments of new sophisticated design. These devices make the analysis very rapid, either as continuous process or discrete analysis. 1.6 Summary. In this unit you learnt about the general perspective of analytical chemistry. Analytical chemistry is concerned with the detection, determination and separation of substances. It deals with the development of methods for chemical analysis. Applications of chemical analysis are to be found everywhere in a scientific and industrialized society. Methods of chemical analysis developed at early stage, gravimetry and volumetry, are now known as classical methods, while those developed mainly in the second half of the last century are known as modern methods of analysis. Analytical methods can be classified in various ways according to the criterion adopted. The major classification gives chemical, electrical, optical, nuclear, thermal and separation methods. These methods can further be classified according to the quantity being measured. Utility of analytical techniques is to be found in various fields as the key to the solution of a variety of scientific problems. It is a chemical discipline with interdisciplinary character, providing valuable information in many branches of science and technology. The recent trends in analytical techniques have followed closely the development of new measuring instruments to find faster and convenient ways for sensitive and selective determination of desired constituents. Instruments can be designed that will automatically perform many or all the steps of an analysis. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.